Okay, so welcome to the afternoon session, and the first speaker will be Zhenghan Wang. So please take it away.
Thank you. I want to first thank the Sakura and the organizers for inviting me here. First time in Oxford, pretty impressive city. So another conference about generalized symmetries. My understanding the word is somewhere related to category theory. But instead of category theory, which I'm doing for a long time, I will talk about dually, which is Hopf algebras and the generalizations. So basically, I will talk about generalization of group symmetries, topological faces in 2D to the most general Hopf algebra you can imagine. So I'll start with a drawing work I just saw missing, came in like a few minutes ago. Time flies. They were still postdoc when this paper was written at Station Q. So this is a drawing paper with Mason, Parsa-Bonderson, and Meng Cheng, and Mason both here. So any technical question, ask them. Don't ask them today. Both came in this morning, so they're jet lag. So I just give you a summary of this theory in one slide. That's what I want to generalize. So basically, the question we addressed in a long paper is suppose you have a two-dimensional topological order, which I define this as a unitary modular tensor category. Another word is Anion model. And then how do you gauge it? And the theory is formulated as Xiaogang-like using numbers. But I will tell you the conceptual way, mathematically thinking, which is much more cleaner. So you have a group. The group you are thinking, we only talk about finite group, don't think about continuous. So take a finite group, take an Anion model, and then you can have the finite group acting on Anion types, their fusion rule, those kind of things. But the Anion model is a braided tensor category. It's a 3 category. So now you can ask, I have a group which is a 1 category. How do I lift this 1 category action to 2 category to 3 category? If you want to lift to 2 category, that's the first obstruction to G cross extension. It's now unique. If it exists, you want to further lift him to 3 category. There's obstruction. Once it's done, there's some choices, and that's it. So that's the theory. But if you are really do in numbers, then we have to scalarize the theory, which means you do everything with a minimum number of objects. And that's the theory called. So you have a modular tensor category invented by Nati many years ago, and now called Anion model if it's unitary of a finite group action. And then you go to extension. This is the adding all the symmetry defects. And then you equivariantize, which means just make it the defect dynamic. And that's it. And there's some very interesting consequences if you do this. This B, which is the input topological order, and the end result of gauging, and they are weight equivalents, which means if you just invert one by complex conjugation, cancel the other one, it's a Drinfeld center. And also, the whole theory is based on a very important mathematical theorem, which many people here are familiar with, which is nowadays, we think about symmetry the same thing as defect. In this particular context, this is a mathematical theorem that all the symmetry form the braided tensor autoequivalence. That as a group, actually as a categorical group, is the same thing as the Picard group, which is the same thing as the group of invertible topological defects. That's a mathematical theorem. But the one I want to generalize today is the following thing. If you have Anion model, if you succeed in gauging it, you get another Anion model, and they are weight equivalents. And the one you get always has a condensable algebra come from the representation of the finite group. If you condense the algebra, you go back to the original one. So that's just a consequence. And this direction, condensation back, that's unique. And the inverse is not unique. The gauging is not unique. There are extractions and there are choices. So The one I want to generalize is, I will give you the definition later, which is something called condensable algebras. And what I want to ask is the question, if you condense, let's go back to here. If you condense the representation kind of, actually, to be really precise, what this is the group algebra inside the category. If you condense that algebra, you go back to your NER model with a finite group action. It's a finite group. And now I want to ask the question, if I condense, instead of the group algebra of the finite group, if I condense a general condensable algebra, what should you get here? It cannot be a finite group. We already know the answer. And the most general thing we can condense is called a condensable algebra, which I'll remind you later. But I want to start with your general thing. In mathematics, how do we generalize a finite group? Well, there's infinite group, there's continuous group, but that's not the direction I want to go. That's too classical, not my taste. So what I want to go is to what's the most general algebraic generalization of a finite group. And the obvious thing is, instead of thinking about group, you should think about the group algebra, because group algebra is quantum mechanics. You just do a linear combination. And group algebra is well-known generalized to Hopf algebras. I assume many people have seen, you have multiplication, co-multiplication, that are compatible. Not a good definition, but that's the easy generalization. And it turns out this is not enough for my purposes. I think I ask, what's the next generalization of Hopf algebras? And that's, remember, a group has a categorical generalization called groupoid. So what is a groupoid? A groupoid is just a category that every morphism is invertible. And what is a group? A group is just a groupoid with a single object. And there's a group algebra, of course, you can take groupoid algebra. And that's an example of a weak Hopf algebra, also called quantum groupoid. So you can ask, okay, maybe I want to generalize to this thing, quantum groupoid. It turns out algebraic, that's enough, actually. We'll only talk about weak Hopf algebra. That's just a small generalization of groupoid algebra. But as I want to do categorically, it turns out there are further generalizations. So what is a Hopf algebra? A Hopf algebra is just take the trivial NER model, which is WEC, and then take the Hopf objects inside that. And now you can take any category, any NER model, take a Hopf object. That's a categorical Hopf algebra. It turns out that's not enough. I need to go one more step. I need to go from categorical Hopf algebra to Hopf monod. Turns out that's not enough. And the final thing I ended will be a weak Hopf monod. And I will give you the definition how to think about later. But the short answer to my talk, which will end, is that I claim when you condense a general algebra, the symmetry you get on the original NER model is a symmetry by weak Hopf monod. And then we go backwards, you should go. It's not unique to go backwards, but that's the answer. I want to convince you. So to do that, I want to say a little bit about this. Is such an honor to have Nati here, because the two things most important to me, the modular tensor category and the VOA, is basically invented by him. So I want to think a little bit about general quantum field theory. So this is not any mathematical definition or anything. So I don't think there's a good definition, a mathematical good definition of quantum field theory that both physicists and mathematicians like. But there are definitions. What I would like to think is that a quantum field theory with symmetry is a pair of algebras. The pair is the local thing, and then there's some non-local thing. You can call global symmetry, but I don't want to do that. Just there's a local symmetry algebra, then there's a non-local thing. And I claim, in general, any quantum field theory at a fixed point should be determined by this. Okay, you should not even separate the two. The two is just a single algebra. It's just you declare part of it local, part of it non-local. That's it. If you think this way, this now goes to mathematics. We all know how to acting on algebra, and that's what symmetry does. Once you know how to acting on algebra, there are two immediate consequences of that. One is, if you know the symmetry on the algebra, that's induced action on the representation theory. And that's also induced a representation on the Hilbert space of states. So this is more fundamental in the sense of a pre this thing you are thinking. So that's what I want to think about symmetry generalized, which is acting on the local algebra. And there are two examples. One is well understood in mathematics, which is you take something called chiral algebra in conformal field theory, and that's mathematician called vertex operator algebra. And you can study finite group on that. That's well studied. And another case is TKFT. And in 2 dimensions, every linear model is a weak Hopf algebra. And then you can ask, how does your symmetry acting on this weak Hopf algebra? That's induced acting on the category. So that's what I want to think about generalized symmetry, which is algebra acting on algebra. I think everything is induced from there. And there are many generalizations. You already see, I think, actually, Meng-Chen tried continuous group. You push in, give you some generalization to high dimensions, but I want to strictly focus on 2D. So everything when I say topological physics, topological order is all 2+1 dimension. So that's the advertisement. So now I want to do the real thing. So first, what is a condensable algebra? I assume you know what is an linear model, otherwise ask Meng-Chen. So suppose you have an linear model. That's a unitary modular tensor category. So what is a condensable algebra? So the thing you want to know is that that's the beauty of a category theory. So what is an algebra? It just has a multiplication, has a unit, and compatible. And you just write down that in diagram. It's a tree. So multiplication, 2 in, 1 out. And then there's associativity and everything. You just write out all the diagram and read that as a morphism in your category. And that's your algebra in your category. Exactly the same definition. And algebra is condensable. So an algebra has 2 things. One is an object of the category, and then there's a structure. And for most physicists, you never think about the structure. You just think about the algebra object. It's not true that every algebra is determined by the object, but the one you see probably won't go beyond this. It's all the object has a algebra structure. So if you have an algebra, then what is condensable? First has to be commutative, which means if you take the braiding, they multiply, the same thing as just multiply. That's commutative. And physicists will call that bosonic, which means every object has a theta equals 1. And it has to be connected, which means the vacuum appeared in your algebra only once. And the most difficult condition is called separable. And the official definition is you have the multiplication from A tensor A to A. Separable means that you have a section, which means an inverse, only as bimodule. It's an inverse as a bimodule. And what is it? This is the most difficult for physicists to interpret it. But for mathematics, it's very easy to understand. That's guarantees semi-simplicity of the algebra, which is a stability for physicists. So that's a condensable algebra. And then if you have one of those in an linear model, you can condense it. You get another linear model. And that's what I want to answer, what symmetry resulting for. And the most important example for you guys to keep in mind is the following one. You take the double of S3, and that's an linear model of rank 8. And normally I label the 8 linears A, B, C, D, E, F, G, H. Not very creative. And ABC is the representation of S3. Actually, I saw it early called 1PE. I don't know where that came from, but I call ABC. So A is the trivial representation, B is the sign representation, C is the 2-dimensional representation. Just take an equilateral triangle and rotate. And then the DE is 3-dimensional, for those who know, and the DE 3-dimensional, FGH 2-dimensional. So that's the 8 linears. If you take the AC, A plus C, A is the trivial representation, C is the 2-dimensional representation of S3, add them together, that's an algebra object, and there's an algebra structure on it. And if you condense it, what would you get? Toric code. So that's the beauty. Okay. If you condense that algebra, get toric code. So this is the example of non-group condensation. And now you can ask, what symmetry on the toric code you get? It cannot be your EM symmetry, that's 2. That's already covered by Z2. if you gauge that one, you get double Ising. You won't get double S3. So that's the answer, the question I will answer in the end. But that example drove me crazy. I thought about it for a few years, just never get it right. I hope this time I did. So, and then I'll give you some contents what happened. So you take double S3, condense A plus C. Normally when you condense, you get two kinds of objects. One is deconfined. That's your linear model you get. Then there's confined. That's your symmetry defects. And there are two symmetry defects, X, Y. And my student calculated the fusion rule for me. So that's a rank 6 category, not modular. It's only G crossed. That's the fusion rule. That's what I show up many times, and it's in many of my papers. So that's the example I want to keep in mind. The other thing I want to keep in mind, I won't touch on this. Anybody here probably is better than me. So what I want to claim is this example of condensation. It's a real condensation. It's not like mathematicians use the word. You can write down some Higgs field, and this is done by Chou Ming-Jian when he was a postdoc. I just asked him. So this is a real condensation in the sense you can write down field and make it work. So although it's not a group, you can still condense and make sense physically. It's basically a coset symmetry. And what we notice is that the algebra object A plus C is not a group algebra, and they are not tensor closed, which means it's not a tensor subcategory, because C tensor C equals A plus B plus C, and there's no B inside your thing. So it's not tensor closed, it's not a group algebra, and I want to invert that one. So now I want to define Hopf monod. I won't give you the definition because this is extremely complicated, even complicated for mathematicians, but I will give you the characterization. So there's a difference in mathematics called definition and characterization. Just give you an example. We all know what is a three-sphere, there's a definition, but I can also give you a characterization which says it's a three-manifold with a trivial fundamental group. That's the same thing, but it's a different definition if you want. So what is a Hopf algebra first? You can say a Hopf algebra is algebra, co-algebra with unit, co-unit, and then with the antipole, they have the following, I don't know, 7, 8 axiom. It does not tell you anything. So what is the characterization? A Hopf algebra, always talk about finite dimensional. A Hopf algebra is an algebra whose representation category is a monoidal category. From this monoidal category to the vector space category, there's a functor. And this functor people call fiber. But what it means is strictly monoidal. That's a Hopf algebra. Many people here wonder about another thing which is irrelevant to me, but I will mention. There's something called a integral linear model. That's like general Hopf algebra. That has to go to quasi-Hopf algebra. So how do you characterize quasi-Hopf algebra? And that's the algebras whose representation is monoidal, has a functor go to VAC, but not strictly monoidal, only monoidal. And that's your co-cycle, anomaly, whatever you call. So that's what it is. And now I can define my most general weak Hopf monod. What is a Hopf monod? It's some algebraic objects in an linear model whose representation category is monoidal and has a functor from this category to the category you start, B. Remember, for Hopf algebra is WAC. Now it's your category you started with, which is separate Frobenius. And I won't give you the definition of a separate Frobenius. What it is that your monoidal category also have an open monoidal structure and they are compatible. So that's a weak Hopf monod. Also, a Hopf monod is not an algebraic object in your category. It's a functor from your category to yourself. How do you relate it back to the algebra? You just take your algebra, tensor everything. That's a functor in your category. So this is a further generalization of that. So, and then area morphisms become natural transformation. You just write down the obvious thing. Really cannot go wrong if you think correctly. So that's a Hopf weak Hopf model. So the only thing really important is the characterization. So you basically just remember, so the generalization is, give me an linear model. What is a weak Hopf monod? It's an induced functor. It's a functor from your linear model to your linear model. And then the representation category of this guy is a monoidal category, admit a functor from this category you start with to, from the representation category of this Hopf monod to the category of you started, and this functor is Frobenius separable. That's what it is. And then in my paper with my student, I skeletize it, which means I write them down with numbers and everything. Actually, that's a lie. The paper did only Hopf monod. We didn't do weak Hopf monod. So that's what it is. And now examples. The first example, David has to cover group. So for group, remember the symmetry means that for each group element, you have a tensor functor from to the category to self. And the Hopf monod you get, you just add them together. Yeah, that's your Hopf monod. And for categorical Hopf algebra, so that means take any category, take any algebra object, and then find enough morphism to make all the diagram is, you just take your Hopf algebra and tensor everything else. That's a induced functor. That's a induced functor. So that's give you a Hopf monod. And the most interesting example would be that you take any tensor functor. And for the case we are interested, every tensor functor has an adjoint. Normally there's a subtlety, left adjoint, right adjoint. In our case, doesn't matter. Just take an adjoint. And then you compose and the target, you compose the right way so that this functor lands on the target, and that's a Hopf monod. And finally, the one I really want to use is condensation. If you have an linear model condenser algebra, the condensation functor is a tensor functor. So that's the example. And so now basically, I want to generalize this. And I did with my student, for two former students, it's published. We did a Hopf monod, and the only thing new I said here is I claim that's generalized to weak Hopf monod. Otherwise, the paper is correct. So don't think I have time to give you, I have 3 minutes, I think it's enough for me to finish. So the first thing would be extension theory. And the most important difficult point is now what's the gradient? And it turns out the gradient is the following. It's an induced functor, and there's an image of the tensor unit, and that decomposed into simple algebra. And the simple algebra is now your substitute of a group element. And then there's abstraction. And the abstraction, you need a cohomology theory, and that's already provided by Davidoff Yeta cohomology of any functor has a cohomology theory, and that's providing abstraction theory. And just give you the example, and then I will finish with a question. So I said, there's this condensation for WS3 to toric code, and the Hopf monod is 2 times E, cancel everything. And in your paper, we give you the structure of categorical Hopf algebra 2 plus E. And for the double theory, it's just the weak Hopf algebra. And I will skip the conjecture. So the last thing I want to say is that this gives you a way to classify or structure for all linear models. So it's a 2-step. First, you classify according to weight class. That's almost understood. And then you ask yourself, within each class, how they are related to each other. And I claim they are related always by gauging weak Hopf monod. So as example, you can ask, how do I classify the weight class WAC? And that's very complicated. That's all fusion categories. And then you can ask, how about the weight class with the Z3? And there are 2 interesting examples, SG2 level 4 and the G2 level 3. And I claim this as a generalization to any odd primes. So this is the last few slides is a little bit quick, but I will just tell you what this is about. I think I still have a minute. Okay, good. I will finish on this one then. I will talk about this conjecture and then why I find this extremely interesting. I claim for each of double ZP Tori code, and there's a non-group symmetry. And when you do the symmetric extension, there's only one defect, X. And when you transfer this X, it's give you all the ZP Tori code plus P squared times this guy back. This is a very interesting fusion rule. And it's called a near group category, which means there's a group plus one object which is not a group. This differs all the things you know about, like Tamagami, Yamagami because of the following. If you look at the fusion rule, for all the gauging group symmetry, take your symmetry defect. When you do the fusion rule, they all go back to the trivial thing. There are no fusion missed between the deconfined and the confined. Now this guy is exactly opposite. When you fuse itself, there's this deconfined, and there's a defect come back with many copies. But this number cannot be arbitrary. There's a mathematically deep theorem to tell you. And I will end by saying there's a long-standing question, which is there's something for double Hopf group, which says is that Hopf group any model exotic? Because that's the only one people discovered. And if this is correct, it's not exotic. It's a family. For any prime, there is one. And P equals 1, you should think about double Fibonacci. P equals 3 is double Hopf group. And I claim for every P, there is 1. Thank you. I think that will stop here. Take any questions.
Questions?
Thank you for the talk. I was just wondering, so annual condensation is defined as a very semi-simple kind of procedure. Did you ever look at what happens when the Hopf algebra is in particular non-semi-simple?
The very reason I came back to this question is I'm thinking about non-semi-simple ones. And there it's very complicated. But I want to mention one thing since you asked the question. I should advertise my student thesis to tell you this what it's about. So I have a student, Aaron Buck-Harry. So mathematically, there are two ways at least how to define condensation. And in non-symmetrical probably it's a little bit messier. So one way is you have your algebra, and then obviously the condensation is just all the modules over that. That's one way to define.
Local modules. Local modules?
Also all modules, it's just all the modules in the category. It's an internal discussion. But there's another way which is much, much better to work with, which is give me any model. But then you have an algebra you want to condense. So what's your new category? And the new category is defined by the following. You never change the objects. The object exactly as the category you have before. What you change is the Hopf space, the morphism between them. So what is condensation? Condensation means this whole algebra now is a new vacuum. So therefore, your new morphism is the old one. If you want to know the new morphism from X to Y, you think about the old morphism X tensor A, which is your new vacuum, to Y. And you declare this is the condensed morphism space. And that's give you the condensed category. And my student wrote down all the details to show those two are the same. And this is known in mathematics, but it's not quite written down in any detail or even correct. I hope I answered your question.
So, I mean, isn't condensing the algebra taking the local modules with respect to that algebra?
So I think the algebra is kind of messy in the sense of once you go to certain things, you have to talk about Morita equivalence of algebra. And that makes it very, very difficult to work with.
I see. Thank you.
So if I have a fusion category, a way of gauging it is by looking at algebras inside that category. Now, if I go to the braided fusion category, there's a condensation completion of it, which is a fusion 2 category. And naively, I would think that maybe gauging is an algebra object in this 2 category. But you're providing another approach here, so I was wondering if they're equivalent.
If I understood your question, I don't know the answer. I think that's exactly the structure of the module category refers to. All I can claim is that any witty class, every two is related by a gauging. But how do you do it? How they are related? I don't even know. There's any way. So it's probably it's a 4 category.
Okay.
There's a question there.
So I have a question about the relation between double of Hag group and the double of ZP. So if you want an RCFT which has this double of Hag group as its symmetries, like confound field theory, is it enough to find some other CFT with the double of ZP symmetry and then do some like restricting the chiral algebra or something opposite to extending the chiral algebra?
If I understand your question, you want to understand the double Hag group symmetry in terms of the toric code symmetry.
Yes, in a RCFT, as a symmetry of RCFT.
Know anything? The only thing I can say is the relation of, I said that if you have a category, it doesn't matter what you gauge, you get another one, they are Morita equivalents. Actually, the theory gives something much better, which is take this one, complex conjugate, tensor this one, it's the double of the G cross. So in a sense, this double Hag group is already inside the double of the Z2 toric code. All you need to do is add the find defects.
Okay, thank you.
So you mentioned that the condensation A plus C go from DS3 to toric code. And then you say there's an inverse of this condensation, like gauging.
Yeah.
So from toric code, you can gauge something to get
it's a Hopf mono.
So what seems toric code?
So I'll give you the examples. So take double S3, and there's A plus C. If you gauge, you get toric code plus 2 defect, which is confined, so I threw them away. You want to go backwards. On the toric code, there is a non-group symmetry, which is take the object E, your electrical particle, add 2, which is 2 times of the unit. And remember how mono is a Hindu functor. And the Hindu functor is just 2 times E, and then take any object, just tensor it, and that's your value of the Hopf monode.
Group like a symmetry in toric code, you can gauge that.
If you get that one, I claim you get a double S3, and there are choices to be made on the way, and that's controlled by David of Yeta cohomology.
I just want to make a comment about Raj's question. So you can think of Hag group and then to condense to Z3.
Double Z3.
And then double Z3, that's right. And then you can actually feed in, say, 3-state parts. And so do what Leo was describing for Hag group. So that's basically something we're working out. But that's maybe an answer to your question.
Yeah, the most interesting to understand is defects, which has this amazing property where your tensor go back to the vacuum in some way. So the main thing about this non-group condensation is when you condense, some objects split into both deconfined and confined. There's an intrinsic relation between them. You cannot disentangle them.
So there's a different way, general way of going back from condensation inversion, QQFT, developed by Runko and Ulivisius.
It's related, but it's...
Can you comment on the relationship?
Yeah, I can comment. That's given me lots of inspiration. So what they did, for those who don't know it, it's a beautiful paper, very complicated. That's why I don't like it. So the way they did is, actually, this is a beautiful thing. I think somebody talked about Ising. They've discovered many Ising in my language, Hopf monosymmetry non-group. When you gauge it, you get SU2 level. No, okay, SU2 level 10. That's on my slide. So it's a beautiful, beautiful thing. For those like Nati, there's no surprising here because SU2 level 10 has something you can condense. There's a conformal embedding symmetry, but the point is the inward. So what they did is take any NER model, you take a Frobenius algebra special, do something, you can get the inverse. They don't have obstruction theory and they don't have extension. They say just do it. So what, in terms of my theory, means is that my Wyckoff monod or Wyckoff algebra will be there. It actually turns out to be a Frobenius algebra because every Hopf algebra is a Frobenius algebra. You just need to change the multiplication or communication. So then you have the obstruction theory. The whole point is about defects. They don't have that theory. And that's what I'm aiming at.
Okay, so let's thank Zhenghan again.